Today's lesson focuses on limiting reactants in chemical reactions. All reactions have a limiting reactant. If you have a decomposition reaction where there's only one reactant, it is obvious that that reactant would be limiting. But when there are two or more reactants, one of those reactants is going to become entirely consumed, meaning that it is completely used up and there is none of it left over. The other reactant will often be remaining or have an excess amount of it present. So the reactant that becomes completely consumed with nothing left over is what we call the limiting reactant. And these are really important because once the limiting reactant is all used up, no more product can be formed. So the reaction will stop once the limiting reactant is totally used up. Let's run through a limiting reactant example, and we're going to do this bit by bit, so with baby steps, and take you through how we solve limiting reactant problems. They are very similar to stoichiometry problems, where those would be a three-step method. Now we're going to add in a fourth step in order to determine which reactant is limiting. So here is a chemical reaction, and notice it says unbalanced. Okay, this is very important that we understand. Coefficients are essential to stoichiometry. So let's take a second here. Notice that we have 2 chlorines on the reactant side. I need to have 2 on the product side. I just changed my sodiums, so I need another coefficient of 2 there. So what will be different now in these types of questions is they're going to start to tell you amounts of each reactant. So notice we have 8.3 grams of sodium, 14 grams of chlorine reacted together. So you haven't seen that before. It's always just been one mass given to you and you being asked to solve for mass or molecules of a different substance. So when we approach these kinds of questions, the very first thing that we have to do is calculate the number of moles of each reactant. And this would be the amount that is available. So let's set this up and solve for the moles of each of these reactants. So we'll start with the moles of sodium, and we are given a mass, so we'll do mass over molar mass, 8.3 grams, molar mass of a sodium, 22.99 grams per mole. And don't round here. We're not being asked to solve for anything. We're just asked to figure out the number of moles of each reactant. The end goal will be to determine the amount of product that we make. But we know that we need to figure out which one of these reactants is limiting or used up. When you do your calculation, you're going to get 0.3610 moles of sodium available. Let's figure out how many moles of chlorine we have available. Again, mass over molar mass. Chlorine is diatomic, so don't forget you have to multiply your molar mass by 2, which will give us 70.90 grams per mole. And it gives us a mole value of 0.19746 moles. Now, these values that we've just calculated are the moles available. Okay, this is how much we have to start with. And we know one of these is going to get used up. This is the whole point of a limiting reactant. And in our next step, we'll figure out which one will be. So let's determine which of our reactants is limiting. And how do we do this? Well, we have to start with those moles available of each reactant. So let's just jot those down. You'll have them on your note. But we're starting off with 0.3610 moles of sodium, and we're starting off with a little bit less, 0.19746 moles of chlorine that is available. So when you look at these numbers, it's obvious that there's more moles of sodium at 0.36 than there are of chlorine. So let's round chlorines down to 0.20. There is less chlorine available. And so if I had a reaction where the coefficients were 1-to-1, I would know it right off the bat that chlorine should be the limiting reactant. I have less moles of it. If I have less moles, I have less molecules to react, or less atoms, depending on your element. But I don't have a 1-to-1 ratio. I have a 2-to-1. And we know that this 2-to-1 means that I need to have twice as much sodium than I do chlorine based on that fixed mole ratio. So sometimes you can look at your moles available and the coefficients and find out right away who the limiting reactant is. And I have a very strong feeling it is sodium, because if I round chlorine down to 0.20 moles, then what should happen is sodium should be twice that amount, and it isn't. Okay, twice of 0.2 is 0.4. I have slightly less sodium moles. But what we'll do is we're going to set this up in a way, again, that should be foolproof, and for you to figure out who the limiting reactant is. So what we do is we set up a mole ratio, and we pick whichever reactant we are interested in. Okay, so sometimes you have a sense of maybe, one is the limiting reactant is going to get used up compared to the other. Sometimes you have no idea. Let's pick sodium because we want to check out, do we have enough of it or don't we to react with all of the chlorine? And so you set up this ratio between the two reactants. And whoever you pick, you're going to use the moles available of the other reactant to compare to. Okay, and then we set up the fixed coefficients out of the reaction, and then we calculate it. So you might be saying, well, what are we doing? Why are we calculating a new amount of sodium? And what we're doing now is we're saying to ourselves, okay, if I reacted all of this chlorine away, okay, all these moles available, then how much sodium would I need? And I would need to have 0.3949 moles of sodium in order to react away all of the chlorine that I have. And when you set it up this way, you compare now how much you need to how much you have available, and you see you don't have enough. And so when your needed is greater than your available, then you know that sodium is going to be the limiting reactant. If my available was less than my needed, then I would know that substance would be the excess reactant. The beauty of this check step, and this is what it is, this is like the fourth step, is that you can set up that ratio with any reactant. It won't matter which one, and you'll always know who is the limiting as a result. Oops, my apologies. If the available is greater than the needed, you would have an excess reactant. I misspoke earlier. Now that we know which reactant is limiting, we can also ask questions about the excess reactant, which we know is chlorine. So chlorine is our excess based on the step previous. And it says, calculate the number of moles of excess reactant required to react with all of the limiting reactant based on the balanced equation. And if we do this, then all we need to do is set this up again so that we figure out how many moles of chlorine are needed to react with our limiting reactant. Well, our limiting reactant is sodium. And remember, we only have 0.3610 moles of sodium around. Don't use the value that we calculated for needed. You need the amounts available. So what we'll do is set that up to our balanced coefficients. So we need 1 mole of chlorine for every 2 moles of sodium. And then the moles of chlorine that we need when we cross multiply is 0.1805 moles. And we know from our previous work that the amount available is 0.19746. And from here, we can ask you questions. We could ask you, how much excess, right? So how much excess is remaining? And that's an easy thing to do. All you have to do is take your available and subtract off the needed, and then you can get the amount remaining in moles or converted into mass. This is a very common extension of this excess reactant problem. So once we know our limiting reactant, we can go ahead and calculate now the amount of product that gets formed. So here they are asking, maximum amount of sodium chloride. And remember, we have lots of data available, and calculated values here, but we have to use the limiting reactant. You have to. So we figured out those moles available of sodium, so 0.3610 mole. This is what we're going to use, and then we're going to mole ratio over to our product and then determine how much we will obtain. So we'll set up a mole ratio between sodium and sodium chloride. And the nice thing here is that the coefficients are the same. So you can set up a ratio if you want, or you can just write due to a 1-to-1 ratio, the moles of sodium chloride equal the moles of sodium, and then write in the value. So 0.3610 mole. Okay, so again, you can set up a ratio if you want. If you choose not to, you have to write a statement like this so that I know that you understand what's going on. And then we're going to just convert our moles of sodium chloride into a mass. And we'll take moles times molar mass, and we'll write 0.3610 mole times the molar mass, which is 58.44. It's a dot. Grams per mole. Now, don't forget, starting data that was given to us for sodium was 2 sig figs. So when we do this calculation, we're going to round to 21 grams obtained. Okay, let's run through an example of a limiting reactant problem. You can try this on your own first and come back and check the answer. If you think you need some extra help, just follow along. So 10 grams of aluminum are mixed with 10 grams of oxygen, and it says how many grams of aluminum oxide are present. This is a limiting reactant problem. They are giving us the masses of both reactants and asking us to solve for the product. We have to do a limiting reactant. So first thing you need to do is to write out your balanced equation. So let's do that. Let's do that right here. So we're going to take aluminum plus oxygen gas, which is diatomic. We're going to make aluminum oxide. Need to know your nomenclature. Aluminum will be a charge of 3, oxygen will be a charge of 2, and we're going to crisscross those charges. You can put states in if you want. We're more worried about the math here. So let's balance this. My oxygens are not balanced. I will put a 2 in front and a 3 in front over here of our oxygens to balance those. And then I have 4 aluminums. I know that the mass of aluminum is 10 grams. I know that the mass of oxygen is 10 grams. This is the dead giveaway that this is a limiting reactant problem. They are asking me to solve for the mass of aluminum oxide. So let's start to calculate this. And remember, this is going to be a 4-step question. And number 1 over here is going to be calculate the moles available of both of your reactants. So let's do that quickly. So moles of aluminum are going to be, sorry, that's a very messy AL, mass divided by molar mass. We know we have 10 grams, and we're going to divide by the molar mass of aluminum, which is 26.98 grams per mole. We get a mole value of 0.3706 moles. We're going to do the same for oxygen. So we're going to figure out the moles of O2, mass divided by molar mass, still 10 grams. And then we're going to divide by 32 grams per mole. So you can never base a limiting reactant on grams because the atomic mass, right, or molar mass of all of these elements weighs different. You always have to calculate the moles in order to know which one is the limiting reactant. So here are the moles available of each of my reactants. We're now going to set up a second step where we determine which reactant is limiting. So when we look at these numbers, we realize that when we determine the limiting reactant, I should be having a little bit more aluminum than I do oxygen based on this fixed mole ratio. I should have 4 moles of aluminum for every 3 moles of oxygen. And I don't have those numbers, I have decimals, but still the proportions should be the same. And when I look at my aluminum and my oxygen, I notice that aluminum is slightly higher than oxygen. So again, it won't matter who you pick to check. Let's pick aluminum and let's figure out how many moles of aluminum we would need. I'm just going to sort of separate that. If I reacted all of the oxygen, so 0.3125 moles of O2 is what I'm going to react away. The molar coefficients are 4 moles of aluminum for every 3 moles of oxygen. And when I calculate the moles of aluminum that I need, based on these coefficients, I get 0.41667, I'll round to, moles needed. And again, I compare this to the amount available. So I have this amount available. I don't have enough. So therefore, I know that aluminum is the limiting reactant. In chemistry, we don't often want a therefore statement, but we do with limiting reactants so that we understand that you guys know which one truly is going to run out first. Now that we know our limiting reactant, we now can focus on aluminum and then calculate the amount of aluminum oxide that we need. We don't care about the excess reactant. They're not asking us about anything related to it, so we just put it off to the shelf for now. So step 3, now that we know the limiting reactant, we set up a mole ratio. And we set this up with our unknown, which is my product, aluminum oxide. And then I compare that to my limiting reactant. And be careful here. You have 2 values. You have this value for your limiting reactant, and you have this value for your limiting reactant. But this is the one you need. This needed is like a fictitious fantasy number, right? It's not real. You only have the amount of aluminum that is available to you, which is 0.3706 moles of aluminum. We set that up with the fixed mole ratio. So we have 2 moles of Al2O3 for every 4 moles of aluminum being used up. We cross multiply, and the moles of aluminum oxide that we are going to now make are 0.1853 moles. Okay, and lastly, we're going to calculate the mass of the product that we should be obtaining. So we're going to set up mass of Al2O3. We know that's equal to the moles times the molar mass. We're going to make 0.1853 moles of it. And then the molar mass of aluminum oxide, 101.96 grams per mole. And I get a mass obtained of 18.9 grams based on sig figs in our starting data. So there you go, a 4-step method to solving stoichiometry problems using limiting reactants.